This talk is actually by my coworker, Marconi Lanna. He unfortunately couldn't, due to a scheduling conflict, couldn't be here to present it, so he asked me to present it for him. And we both work at Originate, and there's a lot of material here. If the talk goes well, it's all in the presentation. If it doesn't go so well, it's all the material. So, but there's a lot of material, so I'm going to jump right in. And hopefully I have time. That's not formatting correctly. It's already going badly. Okay, so I think we all can probably agree Java can be painfully verbose. Meager Hello World takes apparently 129 keystrokes, or 125 if you use tabs, if you indent with tabs. Don't indent with tabs. It is the butt of all jokes. Scala has a very powerful and flexible syntax that lets you write concise but not terse code, very expressive code. A single line of Scala code can leverage quite a bit of JVM power. I actually think a line of Scala code is on average worth 3 to 4 lines of Java code. Slightly paraphrased quote from a really old Dilbert comic strip. I wrote an entire database program using only one-liners. So let's see some of these powerful and elegant Scala one-liners. Using only language features and the standard library. If we pulled in a library like Scala-Z, we could open up a whole new world of one-liners, but these are just from the standard library. And all examples have been tested with Scala 2.11.7 and Java 8 update 51, and apparently they also work on whatever I'm running. So this is not code golf. Not that there's anything inherently wrong with code golf. It's fun, but don't use it for production code. This is not about writing the shortest code possible. Cryptic one-liners don't impress anyone. Code responsibility, right for readability. I think it was Martin Fowler who said any idiot can write code that a computer can understand. Good programmers write code that humans can understand. So keep that in mind. Apparently, it was a lot of fun for Marconi to put this talk together. Hope you have fun too, and maybe even learn a trick or two. I learned a few things going through this talk, which surprised me. I thought I knew everything about one-liners in Scala. Hope you learn a trick or two for very large values of 2. All right, the ultimate Scala one-liner, the case class. Case class? Seriously, case classes? Who doesn't know about case classes? Like, actually, raise your hand if you don't know about case classes in Scala. So everyone. Now, raise your hand if you know for sure everything that a case class gives you. Every single thing. I actually thought I did. I was wrong. There's actually no Scala doc for what case classes give you. Apparently, the default Scala doc page doesn't tell you much. It doesn't give you any of the compiler-generated methods or even the companion object. Even a simple case class with only a few parameters could take dozens of lines of Scala or even hundreds of lines of Java to write by hand. So let's look at everything a case class gives you. You get getters, obviously, we know that. You get setters. If you really, really want them, you can use var, but seriously, don't do that. You get sane implementations of the methods from Java-lang object. ToString basically just prints out a string that could recreate the case class. Equals compares the values like you'd expect, and hash code is consistent with equals. It also gives you can equal, which is what Scala adds to the protocol for equality to make object equality actually work right. It gives you the copy method, which lets you create a copy of the case class instance and change only the values that you want. So you should use that instead of making it mutable. And it gives you serialization and deserialization. It extends serializable and implements read resolve. And it extends product. This is one of the things I didn't know about them. The case class extends product, so you get product arity, product element, and product iterator. I didn't even know those things existed. And in the companion object, you get the apply factory method, obviously. That's how most of us create the case class instances. And then arguably the reason for case classes existing, the unapply, they are called case classes because you use them in pattern matching. And another thing that I didn't know, case class, the actual companion object, go away. The actual companion object implements functions, so you get curried and tupled methods. The downside, of course, case classes can't be subclassed by other case classes. That wasn't always the case. Up until Scala 2.8, you could, and it caused all sorts of problems, and I think they just decided it was the wrong thing to do and just don't allow it anymore. So let's see some examples. And I'm going to run this. So we define our case class person with a name and an age and a flag for whether the person's deceased, but which seems a little bit morbid to me, but maybe it's a Brazilian thing. Marconi's Brazilian, or from Brazil. He's actually international, but lives in Canada. So we can create a person called Jim who is 27 and still living. And then on his birthday, we can replace him with a copy of himself that is 1 year older. And we have product elements, so we can get the values out of this case class by index, but of course it's untyped because there's no way to make that typed. And product iterator will iterate over those things, again untyped. And then because the companion object is a function, you get tupled, so you can take all of the parameters to create the case class, wrap them up into a tuple, and create it that way. And you can also curry it because it's a function and build the person up piece by piece, and then of course apply them all at once. So let's look at some extension methods on Java types. One of the cool things about Scala is you can add methods to existing classes, so that's used in the standard library to add useful methods to the existing Java types. Let's look at some of them on numeric types. You can get the absolute value of a number. You can get the min and the max of two numbers, actually more than two also. You can get the sign num, which is basically it's -1 for negative numbers, +1 for positive numbers, and 0 for 0, which I'm sure that's useful somewhere. You've got methods to create ranges. You can use to create an inclusive range, until to create an exclusive range, and you can even use by after that to change the step of the range. Let's look at float and double. So you have ceiling, which moves up to the next highest whole number, floor, which moves down to the next lowest whole number, round, which moves to the closest whole number and turns it into an integral value, toInt, which turns it into an int by just throwing away the fractional part. You can also convert between degrees and radians. Interestingly, for some reason, if you convert an integer to radians, you get a float and not a double. Not sure why that is. You got some predicates. You can check if it's a valid int, which means it could be converted into an int without losing any information. So only whole numbers that will fit into an int are valid ints. And you also have isWhole, which just tells you whether it has any whether it doesn't have any fractional part. And characters. Char. We've got some extension methods on Arhart. We've got predicates to determine what sort of character, if it's a digit, is it a letter or digit. We can check if it's white space. We can check if it's upper or lowercase. Then we've got methods to convert to lower or uppercase. And finally, you can actually create ranges of characters as well as integers. All right, string. Let's see what it adds to string. You can multiply string by an integer to basically get that string repeated and concatenated as such. You can capitalize a string. You can compare ignoring case. If you have a multi-line string, you can get the lines out. It returns lines returns an iterator, so we'll convert it to a list here to see it in the REPL. And in Scala, a string is a collection of char, and in most ways behaves that way. So you can map over it, you can use exists and for all. So next let's look at array. In Scala, an array is just a Java array. If you create an array, it's just a Java array. But of course, Scala gives you a bunch of extension methods for arrays that make them act like most other collections. So you can map over them, you can get the sum. So let's look at collections. Cool thing, most Java collections can be basically turned into the Scala equivalents. Just import Java converters, import everything from Java converters, and then that gives you as Scala for the Java collections. And it also, by the way, gives you as Java for the Scala collections that can be converted into equivalent Java collections. Useful when you're forced to work with Java libraries. All right, let's look at some idioms common to most collection types. And we'll use as an example collection here is sequence that is the 6th row of Pascal's triangle. So you can, of course, map a function over a sequence. There's a number of different ways to do that. Here we're showing a couple different ways to do it with point-free style, or pointless style if you don't like it. You can reduce. Here we can reduce with plus to get the sum, but you could just use the sum method, better way to do it. Similarly, we can reduce with multiplying to get the product, or just use product. If we define a predicate, then we've got some methods we can work with predicates. We can check for the existence of something that satisfies a predicate. Here, we can check whether everything in the sequence satisfies a predicate. In this case, it doesn't, so we can find out exactly how many items in the collection satisfy the predicate with count. And we can even find the first element that satisfies the predicate. Let's look at filtering and grouping. You can use filter to get only the elements that satisfy a predicate, or filter not to get only the elements that don't satisfy the predicate. If you need both at the same time, you can use partition. You can use group by to turn a sequence into a map. It groups by the result of applying the function to the sequence, and then just gives you lists of everything that fits into that group. You can use take while to get you all of the elements at the beginning of the sequence that match the predicate, and then drop while to do the opposite, give you goes through until it doesn't match the predicate and then gives you everything else. And if you need to do both at the same time, you can use span. And you can even find out, if you were to use take while, how many elements you would get with prefix length. You can check for the existence of an element within a collection with contains. You can find the index of an element from both either the beginning with index of, or from the end with last index of. 15 appears twice in the 6th row of Pascal's triangle. You can use a predicate instead of looking for a specific element with index where and last index where. You can check whether a sequence starts with a subsequence or ends with a subsequence, what starts with and ends with. And you can use contain slice to see if it has that sequence as a subsequence. And you can use index of slice to find where it is. You can get the maximum value from a sequence or the minimum values from a sequence with max and min. And you can even use max by with a function to, in this case, we want to find the max by the person's age. You can use sorted to sort a sequence. You can use sort with to use a different comparison function to sort. In this case, we reverse the comparison to get the reverse sort order. And you can sort by, you use sort by to use a particular function to say what to sort by. And you can, of course, just reverse a sequence. And if you want to reverse a sequence and then map over it, you can use reverse map instead of reverse dot map. Presumably, it's more efficient. You can use grouped to, these next two are a little bit tricky to explain. Groups so grouped in this case with 3, it takes the first 3 and then the next 3 and then the next 3. And slightly different is sliding, which it's like grouped, but it only moves by 1 each time. So you get, in this case, 1 through 3, then 2 through 4, then 3 through 5, and so on. Did I do sliding? Yeah, okay. So we can use that, for example, to find the first 3 consecutive elements whose sum is greater than 40. Considering what that's doing, that's a nice, concise little bit of code there. Make string. You can actually use make string with no arguments and just converts everything in the sequence to a string with toString and then concatenates it all together. If you give it a single argument, it uses that as a separator in the string. And you can give it 3 arguments, which are prefix, separator, and suffix, as such. You can check for intersection of sequences, or collections of any sort, I suppose. You can check for the difference between 2 sequences. You have actual sets in Scala, so proper sets, so you can do set union. You can check whether a set is a subset of another set. You can get all of the subsets of a set, including the empty set and the set itself. Or if you only want the subsets of a certain size, you can give it an argument. In this case, we only want the subsets of size 2. You can find all the combinations of a sequence, all the permutations. And you can get only the distinct values. You can remove all the duplicates with distinct. And you've got this interesting thing called corresponds, which takes a binary function and then checks whether corresponding elements between the 2 sequences all satisfy that predicate. In this case, they do. And you can transpose a sequence of sequences. This is, it's exactly the same as matrix transposition. Okay, lift deserves a little bit of explanation. So a sequence is actually a partial function of its index to its values, which it makes sense. A function is a mapping from its domain to its codomain. A sequence is a mapping from index to value. So it makes sense that it's a partial function. Lift takes lift is a method on partial function that lifts it into a total function that returns an option for. So it returns some value for all the values for which the partial function is defined, and then none where it isn't. So if we can use lift to try to get something from an index, and if it's not there, we just get none. Parallel collections. We've got parallel collections in Scala. They behave, for the most part, exactly like sequential collections, except that operations are performed in parallel using all CPU cores or as many CPU cores as make sense. So we do that by we have the .par method, which turns a collection into a parallel collection. And now it's kind of hard to, you can't really tell, but sum and map actually work in parallel now to compute this. So presumably that probably didn't go any faster. But if you had a computationally expensive function you were mapping with, they would. We can use for each here to sort of demonstrate that it's actually doing this in parallel, because every time we run it, we get a little bit different order. All right, let's talk about maps. So with maps, you have a function called get or else, or a method called get or else, which if the value is not in the map, if the value is in the map, you'll get that value in a sum. Otherwise, you'll get I'm sorry. That's what get does. Get or else will give you the value, or if it's not in there, it'll give you the default value that you give as or actually the default expression you give as the second argument. And you can, in addition to all of the normal collection methods, with maps you can do things with just the keys or values, like filter just the keys, or you can map over just the values. And you can use a mutable map as a very simple in-memory cache using the method get or else update, which is like get or else, but if it's the or else, it actually puts it into the map, so the next time you'll just get it out, which we can see here. We've put, we didn't have, let's see, I forgot what the demonstration here was of the, oh yeah, get or else update B with bug, because the B was already in there, we got B. Okay. You get the idea. All right, let's look at streams. No one-liner talk would be complete without a Fibonacci implementation. Or 3. So here's one. Gives you a Fibonacci sequence. Here's another. This one's actually my favorite. This is, can you see the cursor? This here is actually basically the complete Fibonacci. Well, I guess since it's recursive, you need the whole line, but that's a pretty short Fibonacci sequence. Implementation, which obviously works. And then this one, using stream.iterate, it's a little more complicated. I don't like that one as much, but those are 3 different Fibonacci implementations that are all different than the one I knew. So, all right, how am I doing for time? Cool, I've been blowing through this. Every time I practiced it, I ran out of time when I got to this point. Okay, putting it all together. We've got supposedly a pangram. The quick brown fox jumps over the lazy dog. That supposedly has every letter in it. Does it really? Let's check. Let's use for all. And for all says it does. But Marconi's very skeptical. He won't believe it until he sees it. So let's use distinct and sorted to actually look at all the letters. And look, there they are, A through Z plus a capital T and a space. So how many times does each letter appear? Oops. So we can group by to lower the letter, we can group by to see that it's kind of hard to see. Well, I mean, we can see that E appears 3 times because we see 3 E's. Let's actually compute the frequency of each. There, now we actually see it as a frequency. Space appears 8 times. Now let's remove the white space and save it in a value, so we have it for the next slide. We can sort it by frequency here. Nice. Now we see that the most frequent one is at the end. O is the most frequent with 4. But we want the most frequent first, so let's sort it with the opposite comparison. And there we see at the beginning O followed by E followed by T. And let's only look at the letters that appear more than once and then format them nicely. Cool. Let's find all the words with the letter O. So we'll use split to split on white space or split on space to get all the words, and then filter those for just the ones that contain O. Brown, fox, over, and dog. And let's look at all strings that contain at least one of a set of keywords. So here we've got some maybe hypothetical headlines. Let's look for the ones that contain either Scala or Swift or both. And Java 9 delay does not. All right, let's plot a horizontal chart of our Pascal triangle 6th row. So that's pretty cool. We actually graphically see the numbers in the row. Let's add some value labels. Cool, 1, 6, 15, 20. Now let's make it vertical. Pretty cool, but I'd like to actually see all of the stars. Can you spot the difference between these two? Anybody? Here, let's make it so everybody can see it. Yeah, just equal versus greater than equal. So then we get a proper chart like that. So let's use some negative numbers. Here we're going to plot a sine wave. That's pretty cool for that little bit of code, huh? And we can do the same with cosine. All right, extension methods. This is how we actually add our own methods to some, what am I doing on time? This is how we add our own methods to some existing classes. So here we have stars. We can add to int to just get a set of stars, or a list, or a list of stars. We can add isBlank to strings if there are any Rails programmers out there. This active support does this for Ruby strings. So it's isBlank if it contains nothing but white space. Cool. We can read the contents of a file very easily. We've got a file here with a bunch of characters from The Simpsons. We can process a file line by line using getLines on the source. Let's print them out with line numbers. Cool. We can select a line at random with random.nextInt. Cool. We can run this several times and get different characters. And we can fetch a line from the web. See, hopefully my internet connection is working. Great. And we can read the news. We're going to read some XML. Apparently that's a theme at this conference, and we need some XML in every presentation. But we don't want to actually read XML. XML is not as human readable as it was advertised. So I want to see just the headlines. Cool. And importing instance members. So we have our person Jim here. We can actually import the instance members of that and just refer to them as name and age. There is a method in Marconi's randomness, plenty actually. We actually don't remember what this is about. Oh, just a bunch of next ints, I guess. Next doubles, get a bunch of doubles. We can get normally or Gaussian distributed values. We can get booleans, get random booleans. We can get random printable characters. Pretty cool. We can get a random next string of a certain number of characters. This is interesting. We get characters like that pretty much every time. But if we only want alphanumeric characters, we can just say random.alphanumeric. I'm actually not sure what random.alphanumeric by itself returns. Is that an iterator of some kind? It's a stream. Okay, cool. Even learned something just now. All right, you can shuffle. Sequences. And another thing that I learned from this presentation, you actually have console colors from this console thing. So now we can actually make colorful stuff. Preconditions. You have a thing called require, which you can use for preconditions. This is very similar to assert, except it throws a different kind of exception. You use require when to use a web analogy, exceptions thrown by require are kind of like 400 errors, whereas assert would be like 500 errors. Assert asserts things that should never happen. So now if we try to create a person with a basically only white space as a name, we get an exception, or with a negative age, we get an exception. All right, regular expressions. Regular expressions are very easy to create in Scala. You just add .r to a string. But you want to use triple quotes so you don't have to escape all your backslashes and want to kill yourself like we did in Java. You can extract, this is a really cool thing. Regular expressions have an unapply method, so you can use them as extractors. Take that, Perl. Now let's parse some numbers. Here parse some string representations of numbers. Cool. And we can even run system processes. More stuff that I didn't know before this presentation. You can import this Scala sys process dot underscore, and then you get things like bang to run a string as a shell command. In the shell, you can use bang bang to capture the output. Very cool. And you've even got you can even do piping and ORing just like you can in a shell script. I completely didn't know anything like, I couldn't even imagine this existed. Very cool. All right, and I got through it. Excellent. So this talk is actually on GitHub at that URL. And if you liked this talk, you may also like other talks from the same author, Idiomatic Scala, Your Options Do Not Match. It's kind of a rant about, among other things, using using options and pattern matching. He gave that as both a talk and a blog post on our Originate blog, and there are lots of other great blogs on blog.originate.com. And somebody already asked even before the presentation about this thing I'm using to do the presentation from a REPL, and that's Marconi. That's a thing Marconi wrote called Represent, which is on GitHub. It's very simple at this point. I'm sure he would love pull requests. And thank you very much. Any questions, comments? Pretty straightforward. All right, great. Thanks, guys. Enjoy lunch.